All right, we got streaming, and oh, there we go. All right, we got the other mic on, um, and it's recording, so we're good to go. So I just want to remind you that the family or the cousins homework is already up. And I basically just typed up what I said the other day. Um, Basically, you want to use SWI Prologue to specify a whole bunch of parent of clauses to reflect the actual parenthood relationship between the elements of the universe. So each clause is going to look like this, okay, depending on the names of the people that you want to document in this particular program. Um, and you will need 4 generations. So you need a tree, not necessarily a tree, but you need 4 generations of ancestry in order to get this program to work. Because I want to be able to test up to second cousins. Okay. Then you need to do the more complicated one because the more complicated one is to define the cousins clause. Now, this is not how you want to write your clause. This is how you test your clause. So the way you write your clause is they would be rules like cousins, and then you have x, y, and then z, and then the rule would expand to some conditions, and you will need multiple clauses too, because it's going to be slightly recursive. Okay, so you need to provide the base case first, and then you work from the base case. If you want to, you can consider siblings as level 0 cousins. A normal cousin is going to be like first cousin, and then the second cousin would depend on the first cousin, right? So are we okay so far with the description of the homework? We good? All right. So you have to use exactly the names of parent of and cousins because otherwise, it will be difficult for me to test your code. So you have to make sure that you use those names exactly. If you need some other clauses to make your cousins work, you can use any name for those extra clauses because I won't be testing those individually. And the last part here has to do with it's helpful that you use actual members of your family for at least for testing purposes, okay? Because you can tell, right? I mean, who are your second cousins, who are your first cousins, who are your siblings. So for testing purposes, you can use actual names, and if you want to preserve their identities, you can just change those names to just A, B, C, D, E, F, and so on. So you don't have to submit your homework assignment using real names, because I have no idea whether John really is your second cousin or not. Okay, so they have no meaning to me. But when you're debugging, it might be helpful to actually use real names so that you can test your program more and validate the actual output of your program. And there's one single thing that you have to turn in, which is the Prologue program. It has to be the one with a PL extension. It, if you write a text file without the PL extension, the SWI Prologue is not going to accept it anyway. So you have to use a file that has a PL extension. So are we okay so far with the homework? What you're supposed to do? Okay. And you will have to use the recursive definition, which we learned from the factorial example. We'll also have to use the backslash plus, which is the not thing that we also need. We also need that because you want to be able to differentiate siblings from cousins, and to do that, you have to basically say they do not share the same parent. So you have to find a way to specify they do not share the same parent. Now, if you want to, you can also add additional clauses like no share parents XY. Okay, it returns true if and only if those two do not have the same parents. Okay, so you can have helper clauses to make your job easier. So are we okay so far with the prologue, which is going to be your last homework assignment? So that's good. Okay. All right. Yep. Say that one more time. If prologue is on web. Oh, okay. That I do not know. So we can, okay, we can search for it. So web-based Prologue. Okay. SWISH. Looks like there's something like that. Create a Prologue here. Okay. Program. Yep. Looks like you can do it online. And then you can test your query here. Let's give it a try. And it's based on SWI Prologue, which is exactly what I used in class. So you can say is a Jedi Luke Skywalker. And then over here we can ask is a Jedi X. Oh, Control Enter to execute. Yep, there you go. Nice. So there we go. So you don't have to install. And if your phone has enough resolution, you can probably do it on your phone. You can do the whole homework, as homework assignment on your phone. The question is, it does allow you to save the file, right? There you go. So you can now save the file and then submit it using Canvas, and you're done. So you don't have to install anything locally. Good idea. Except this won't work when you do not have internet access. All right, cool. Good discovery. Anything else? Any other questions related to the homework, the Prologue homework? No questions? Okay. So if there are no questions about the Prologue homework, we're going to go back to the homework, the Prologue slide, and continue to talk about one more item in that module. So that's basically the mechanism of Prologue. How does it match stuff, right? So when we go to predicate calculus, opens up a module, and so it's this stuff, that is kind of important, the substitution part. And we want to kind of get back, let me see here. So this is the good part. Okay, there we go. All right, so there are a few things that we can review in this case, because what we want to do is to go back to what is a proper Jedi, based on the rule. So we can see both at the same time. This is the rule that says, who is considered a proper Jedi. And this is the actual mathematical symbol or mathematical expression to say exactly the same thing. So we just have to remember that x and y are variables that actually, no, only x. Only x is a variable appearing on the left-hand side of the rule, and that is the only one that is universally quantified in this case. The y is only appearing on the right-hand side, and that's why it is existentially quantified. So we only have to find a single y in the universe that satisfies this requirement, but we need every x in the universe to find its own y to satisfy this requirement. Is that okay? And the rule is specified, in an opposite order. Whatever is on the right-hand side of the rule becomes the left-hand side of the implication, and then the name of the rule itself is now, or the head of the rule, they call it the head of the rule, it's now the second part of the implication. Is that okay? All right. But it doesn't solve the problem. It doesn't answer the question of, so how does Prologue find which x and which y to test in order to get this to work? So that mechanism is the substitution mechanism, which we briefly described. So what we do is we are extracting only this part out, okay, without the quantifiers. So we're only extracting this part out and call this phi, okay? And the way Prologue works is it will try to satisfy this requirement by substituting x, which is a variable, and y, which is the other variable, with actual atoms. And substitutions, basically work this way. So a substitution it looks like this. Each item in this particular set S is called a mapping. So we map X to Luke Skywalker, and then we map Y to Anakin Blue. So that is called a mapping. But when you look at the set as a whole, it is called a substitution, which basically means when we combine those two, when we say phi s, it is applying the substitution to phi, and all it's doing is it replaces every single x or any reference to variable x with Luke Skywalker as the atom, and then it replaces all the occurrences of y with Anakin Blue. So after the application of the substitution, then we end up with this particular result, and this result can be evaluated to either true or false. Are we doing okay so far? Okay. So after the substitution, we can see that Luke Skywalker is in fact a Jedi, and Luke Skywalker owns Anakin Blue, and Anakin Blue is a lightsaber. As a result, it's implying that it's a proper Jedi is also true. Because with any type of implication, if the left-hand side of the implication is true, if the implication itself is known to be true, which is what is implied in the rule, then the right-hand side of the implication also has to be true. So this is the lowest level of mechanism for Prologue to work, is substitution. Is that okay? And the way it looks for substitution is not really looking at all the possible atoms in the entire universe, because that will take too much time. So the way it works is it will look into is a Jedi, and it will go through all the is a Jedi clauses from top to bottom in exactly that order, and then once it finds one, then it will move on to the second one and ask, okay, if X is Luke Skywalker, can we find any clauses of Luke Skywalker owning something? And it will find all of those, okay? And then for each one of those, it will bind Y to one particular atom based on the owns clauses. And then once this condition is satisfied, then it will go for the third one and check whether whatever is used to substitute Y is in fact a lightsaber in that particular order. If one clause fails, for instance, if let's say we have another a Star Trek universe item person here, name one person who owns nothing in in that universe. Okay, we'll say Chewbacca, and Chewbacca owns nothing. Okay, so it will first, but Chewbacca is not even a Jedi. Name a Jedi who owns nothing, not even a lightsaber. Hmm? Yoda still had his lightsaber when he died, when he passed away. At some point he did, but at the very end, I don't think he had a lightsaber anymore, or at least the movie never showed it. So we'll just say that we're talking about old Yoda, okay? So Yoda is a Jedi, okay? So it satisfies that requirement. But since Yoda does not own anything, we cannot make the owns clause true. Then it will backtrack and say, okay, is there anyone else who is a Jedi? That is the built-in mechanism of Prologue. It can backtrack. Once it evaluates this whole sequence and it finds something is false, it cannot made true, then it backtracks to the previous one and say, okay, is there any other way to make this one true? And then we'll move forward and test again. So it would basically do an exhaustive search for all the possible answers, but it will do it in quote unquote a smart way, so that it doesn't really test every single thing in the universe. It will only use the clauses that have that mentions elements of the universe. So that's kind of the engine of Prologue. It's really interesting. Once you get into it, you can convert any algorithm into Prologue, including merge sort, quick sort, that sort of thing. Except the program is not going to look like anything that you have seen before. You will probably get to Prologue again in a upper division class at a four-year university called programming languages. Where they examine all kinds of obscure and strange programming languages. Lisp would be one usually, especially if you go to Berkeley. If you go to Berkeley or Stanford, I think Lisp will be introduced pretty early on in the computer science curriculum. Prologue is another one that many programs would mention, just because of the ability for it to backtrack and look for answers. So you will see this again, more likely than not. So do we have any questions about this? Yep.
So on the other side of the implication, is
Uh
it
huh.
proper Jedi is already true, and we're testing to see if everything on the left side of the implication is true?
So every if okay, so the way it works is if you can get this entire part to be true, then we basically say is a proper Jedi is also true.
Okay. But it only takes one to make the implication. It only takes one on the left to
No,
be false in order for
to make the entire thing false. Right. Yep. It would take all of those to be true in order for the right hand side to be true, but it only takes one to be false for the entire thing to be false. You're correct. Yep. All right. Any other questions? No other questions? All right. So try to make use of the resource that we just found, which is this thing here. I'm gonna put a link, to on Canvas, just so that we have that as a resource now. Okay, let me go down to the Prologue or predicate calculus module, and then add a external URL, and this is the web version of SWI Prologue. Load in a new tab, add item, and make it visible. So now you guys have access to what we just used a little bit earlier, which I think is a great resource. So thank you for asking the question.
You actually misunderstood my question, but this is great.
Okay, if I misunderstood your question,
I was asking if it was on one specific website, but this works even better.
oh, okay, so with my misinterpretation of your question, the answer actually made the original question unnecessary, made the proper answer to your original question unnecessary. Okay. It works out, yes. Yeah, that's all we care. It works out. Good. Okay, so we are pretty much done with all the material for this class. So the rest we can for the rest of this entire semester, which are the rest of today's class, Monday and next Wednesday, we can do review. So next Monday for sure we'll start with practice final exams, and we'll go through some of those questions. Yep.
we do have class next Wednesday.
I do not know. Yes.
Oh, so I was gonna ask you about the lab that was due today, and then some about extra. Can I ask that right now?
Sure. If it is a question that applies to more than one person, I mean, go ahead and ask anyway.
Okay, so first one is for it's all submitted, so I can say it, right?
Mm-hmm.
Okay, so there was two paths. Well, I think there was multiple paths to get to the answer. Um, so in the dissert algorithm, you pick the shortest one, right? So if you have multiple shortest paths, okay,
Mm-hmm.
are you supposed to just pick one or put all of them as an answer?
Well, you will if there are multiple. Yeah, go ahead. Hmm?
It's just how the algorithm runs. If they're comparable, it's just gonna pick one.
Yep. You just rent. You can pick
Because it's
one
not,
if they are
because it doesn't pick them if they're equal, it just skips over it.
right. So if there are two paths, you found one of the shortest paths already, it would not choose the second path because the cost or the distance of the second path is not less than the first one.
So it would just choose
Hmm?
the first quickest pass over the second quickest pass.
Just
Let's say they're equal. It would just choose the first one
It depends a lot on how you found it. So okay, so let's go through an example, and we'll use Zernal for this. It is all about the algorithm, okay? Because we are not trying to find the shortest path by hand. We're trying to follow the algorithm, and there's only one part of the algorithm where you can toss a coin, okay? If two vertices look just as promising in the set Q, then you can choose one or the other. And that is the only part where you can say, okay, I can choose this or I can choose that. You get to decide that. Well, because you're the machine. You're running pseudocode, and so you are the processor. So you get to toss that coin and say, okay, since these two vertices are just as promising, and they're the best, choices, then you get to choose which one. But I can show you an example where that will not happen. You always find one first, and then you will never find it. You will never choose the second shortest path. Okay. Okay. So the example is going to go like this. Okay. We have, this is our destination, D. We got, A, we got B, and then we got C. Okay. And I'm going to use double circle to indicate this is our destination. And it goes like this. Okay. And this is 2, this is 3, this is 3, and this is 2. Okay. So the shortest path that Dijkstra's algorithm will definitely choose is going to be A, B, D. Okay, it would never choose the shortest path of A, C, D. Even though both paths give you the same distance, because of the way that the Dijkstra's algorithm work, it will always expand B first, because B looks more promising than C does. So in this case, even though there are two paths that are of equal length from A to D, Dijkstra's algorithm will only construct the path of A, B, D, and not the other one. Now, it will have the edge from C to D, because if you look at vertex C, what is its shortest path to one of the destinations? Well, okay, CD is the shortest path. So the edge CD will be in the solution, will be in E prime. But when you look at A's perspective, then it's going to be AB, that edge is going to be in E prime, and then BD would also be in E prime. So in this case, even though there are two identical distance paths and they're both the shortest, Dijkstra's algorithm doesn't even have to choose. It always makes it a certain way.
It would choose the other one on the way back.
On the way back.
From A to D, or from D to back to A. Yeah, it would choose the opposite one.
So it would choose, this will always be in the solution, this is always going to be in the solution, and then it will expand this one.
Right.
Yep.
And then if you switch the destination and the start,
Yeah.
it would choose the opposite.
Correct. Yep. Yep. Because it's a greedy algorithm. So is that answering the question, or is it kind of giving you an idea of one scenario? Now, on the other hand, if your scenario is more like this, okay, if your scenario is this is A, this is B, this is C, and this is D, okay, C. And this time we actually have identical edges like 2, 2, and 3, 3. Then this time it would choose one or the other, because it would expand D being the destination, it would expand B, C at the same time. But because B and C both have the same L value, so the algorithm would go like, okay, we have two vertices in Q and they have identical L values, then you can choose either one. So in this particular case, depending on which one you choose, then you can end up with having AB in the solution graph, or you can end up with AC in the solution graph, depending on which one you choose. So it depends. It's not because that we have shortest paths of the same distance. It has to do with the expansion of the vertices when we encounter those vertices in the set Q. So are we doing okay so far with this? Yep.
Are you gonna post the solution for the homework before the test at all, or?
Well, let's work on it today, since we got time, right? Okay. All right. So,
I want to ask you about that, the previous again,
which one?
the one that you put.
Oh,
I want to ask again. So why does it choose A to D and D to B? Because
with the bottom one or the top one?
yeah, the top one.
With the top one. Okay. So if you think about the top one, we with Dijkstra's algorithm, we start with the destination. So D is the only element in Q initially, right? And then we look at all the incoming edges into D. We got two incoming edges, BD and CD, right? Then we will look at BD and say, did we just find a shorter path for B? Yes, because initially L of B was infinity. So we did find a shorter path for B. So we will put B into the set Q. But in the same for each loop, we are not getting out of the for each loop yet because we have another edge CD that is also an incoming edge into D. Then we're adding C into the set Q as well. So at that time, okay, then we're done with the for each loop. We get back to the while loop. So the while loop would say we're not done yet because we got two elements in Q. Then it will choose B because B has a lower L value. Yep. So that's why. Yep.
Question.
Mm-hmm.
We've done examples where we always have like one starting point A. Does it matter?
No, there's no one starting point. Remember, in Dijkstra's algorithm, you do not identify which vertex is a start vertex because it will find the shortest paths from each vertex to the closest destination. Right, so with A star, we have to designate one start vertex and one destination vertex. And this one works backwards, yes. It's not like the algorithm that Iraj talks about in cisp440 because I think the one that he uses start with a start vertex and go forward to the destination. But then it can only find the shortest path from one vertex to a destination. It doesn't do something like this one does, which solves all the shortest paths from every single vertex. Okay, so are we okay with this? Good. Okay. So now we go back and look at the homework assignment, and we will just work that one out. All right. So here we have the text description of the graph. So do you guys want to look at it from the graphical perspective, or do you want to look at it from the spreadsheet perspective? Both?
That's how I did it.
Yeah, we could do that. It's just a lot of work to do it. Huh? Okay. Well, first of all, let me make a duplicate of this spreadsheet first. So,
Without like the graph.
so we want to make a copy. There we go. And we'll call that solution of homework. And then we have to, it would be nice if we can show both at the same time. So I'm going to do some editing here. And then we'll erase a bunch of cells because we are starting from scratch. Okay. All right. So the destinations are, let's see. Did I specify the destinations? D. Okay. Okay, gotcha. All right. So we can now run the algorithm. So do you guys remember the algorithm, or do we need to display that too? Because I'm running out of space on the projector. We're good without the, okay, all right.
Somewhat okay. Yeah.
Yep. Okay. So the initialization, okay, is going to be E is going to be an empty set to begin with. VW are not relevant at the first part of the algorithm, and all of these are infinity except for the one that is the destination. So D is the destination, you said? Okay. So that's the one that has a 0 and everything else has infinity. We don't have E. Yeah, so we can just cross out this thing. So we just delete. There we go. All right. Okay. So now we can actually get into the algorithm. So the only other thing we have to initialize is Q starts with the destination vertex, which is D. And now we have to choose which vertex in Q inside the loop. Since we only got one element, we don't really have to choose. D is the one. And now we have to look into incoming edges to D. And there are 3 of them, AD, BD, and CD. Okay, so we know that we can actually pre-populate the W's, because we know W can be A, can be B, and can also be C. So when W is A, we're looking at AD, the edge AD. The edge AD has a cost of 10. So, but 10 is good. It's still less than infinity. So we found one path to a destination compared to not having a path. So L of A is now updated to 10. Oh, by the way, once you choose something, you have to remove it from the set. But now that we have determined that A has a new L value, it is now added to the set Q. We look at B, and B used to have an L of infinity, and now it has a L value of 3, and that's less than infinity, so we have to update that, which also means we have to add B into the set. When we look at C, kind of the same thing. C used to have an L value of infinity, and now it has a L value of 1, and then we're going to add it to the set as well. So now we have A, B, C in the set Q. That's the first iteration through the while loop. So are we doing okay so far with this? Okay. So we get back to the beginning of the while loop, and we ask, well, do we have an empty Q? Nope, Q is definitely not empty. It has 3 elements. So we have to get into the while loop again. So this time we have to be a little bit more careful when we choose. Oh, I forgot one thing, because I forgot to update E as we add those things. So we have to keep adding those edges. So we have AD added to the E prime set, and then now we have AD and also BD added to the E prime set, and now we have AD, BD, and CD in that set. Okay, I almost forgot. Okay, so getting back to the beginning of the while loop, now we have to choose a different V based on which one looks the most promising. And if you just look at the L value, it's pretty clear that C looks the most promising. It has the smallest L value, so we choose C. Now we have to look at, and then we remove it from the set Q, so we only have AB left in that particular set. Now we have to look at all the incoming edges to C, and let's see. C has only one incoming edge that is coming from B, so we have to evaluate just that. So here's B. So now the question is, the edge BC has a cost of 2, and when you combine the L value of C, which is 1, it is 3. So how does that compare to the current L value of B, which is also 3? It's not less than. It is the same. So that means we are not adding B back into the set. Well, it's already in the set, but we're not doing a single thing. There are no updates to E prime, no updates to any one of the L values. Is that okay? So then what we do is we are done with the for each loop. We get back into the while loop. The while loop looks at the Q, the set Q. It is still not empty. Now we have to choose between A or B. A has an L value of 10, B has an L value of 3, so B looks more promising. So we choose B over here, and then the set Q becomes just A by itself. And now we have to look at all the incoming edges to B. According to E, the only one incoming edge to B is AB. So we have to evaluate the edge AB. And now the question is, did I just find a shorter path from A to a destination? The edge AB, okay, has a distance of 1. When you combine that with the L value of B, which is 3, you get 4. In other words, we just found a path with a length of 4 from A's perspective. And you compare that to what we already know, which is 10. So we say, okay, we just found a shorter path. Let's update the L value. But you also have to update the E prime. And the way we update the E prime is we get rid of the AD first. And so we have, so technically speaking, there are 2 steps. So the first step ends up with just BD and CD in a set. And then the second step is adding back AB to that set. So there we go. And we also want to add A to the set Q because we just updated the L value of A. So we have to add it back into Q. But since Q already has A in it, it doesn't look like we have done anything to Q. But I'm putting it again into the Q column just so that we know that there's an operation, except its new value is the same as the old value. Okay. All right. And then we are done with the inner loop. We get back to the outer loop. The outer loop looks at Q and say, is it empty? Nope, it's not empty. We cannot quit yet. Now we have to look at all the incoming edges to A. A has no incoming edges. And as a result, well, I have to back up a little bit. We have to pick A because it's the only edge, the only vertex. And then once we choose a vertex out of Q, we have to remove that particular vertex out of Q, and we're done. Because A has no incoming edges, so we have no W to examine, and then we are done with the while loop. We go back to the beginning of the while loop, and the beginning of the while loop says, oh, Q is now empty. We are done. Yep.
In the very beginning, in the first iteration of the while loop,
Mm-hmm.
you chose vertice A as your W first. That you didn't have to choose vertice A as your W first, correct?
With which iteration?
The first while loop iteration. So after we take D out of Q.
Uh, This is the first iteration of the while loop. This is the second while loop iteration. This is the third. This is the fourth. Huh? The
Like,
third.
you know how you picked A first and then B and C? It wouldn't have mattered if you picked B.
Oh,
first.
these
Yeah.
3? Yeah, these can be reordered. It won't change the end result. So we'll still end up with these in E prime, regardless of how you reorder these. So rows 4, 5, and 6, really do not interdepend. There's no interdependency between those 3. Yes.
Line number, it's number 8. So you're only updating a path when it's more than, right? Or like for your
When you find a shorter, when you find that the new path has a shorter length, then you have to update the L value. And when you update the L value, you also have to update E prime, and you also have to update Q.
But when they're equal, we just keep the previous one.
Correct. That's what the algorithm says. Because when you look at the algorithm, okay, so let's go to the algorithm itself. So as far as this homework assignment is concerned, other than the ordering of the for each, nothing else really has a choice. It's like you have to pick this one based on the algorithm. So let's go back to look at the algorithm first. So we are looking at graphs. And Dijkstra's algorithm. So when you look at Dijkstra's algorithm, this condition here, says if the combined if the sum of L of V and the distance of the edge that we are looking at, if that is less than what we know about, is the length of the shortest path from W, then we do the following. So when these two numbers equal to each other, then we don't do a single thing because the condition would have returned false. Is that okay? All right. So are we good with the solution of this homework assignment? All right. Cool. Anything else you want me to go over? Oh, what about that one? The one that finds all the not permutations, find all the combinations. Remember that homework assignment, where you have to list all the, huh? Yeah, the omega generator thing. You guys want me to go over that one too? Okay. So let's go to the homework description first, because that's where everything starts. Question is, how long do you think I need to write that program? I don't know. I haven't written it yet. No. Okay, so that's counting. It's the U generator, not the omega generator. It's the U generator. Omega for permutations, and then U for the combinations, right? Okay. All right, so we'll start with this one. I'm just thinking about, should I use VI on the command line, or should I use mouse pad? I'm gonna use VI. I just feel a lot more comfortable with VI. Okay, so all right. So we need to do main first. Okay, so main has argc and cons char star star argv. And I'm going to do some type checking here. If argc is less than 3, I would just print an error message or just quit. Okay, just do nothing here, because we need at least 3 arguments. The first one, argv0, is the path to the executable itself, which is not useful to us, and then we need the other 2 to be useful. And I need to convert those strings into an integer. That's ATOI's job. So I need to look up how to use ATOI. Okay, so pound includes standard library. We give it a string, it gives us an integer, and we're all good. Okay, cool, easy peasy. So pound include stdlib.h. How many people wrote this program in plain C, and how many people wrote it in C++? Plain C. Anyone did? No one did it in plain C? Okay. So most of you did it in C++? Okay, all right, that works too. All right, so we need to keep track of that. So we need an integer to keep track of, what was the first one? The first one is number of trials. Okay, so we need number of trials. And that is going to be, if I'm not going to do any type of error checking, I just give it, argv bracket 1. And then the second one is number of choices. Okay, so num choices is ATOI argv of 2. Okay, so now I know how many trials, and I know how, what the number of choices for the first trial. And then the rest is just saying that everything they have to be represented by lowercase letters, and the number of the choices can range from 1 to 26, blah, 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 blah. And we want to look at combinations. Okay. So what makes this program actually easier than the omega generator is you can do it in a sorted way, because ordering is not important. So you can basically say, if you have to choose between AB and BA, if AB has happened already, has been printed already, then you don't have to print BA. Is that okay? So that means if the elements are out of order, they're not in an increasing order, you can just ignore that. Okay? So that really helps to make it easier to write. So right here, we can go to the beginning and write the actual subroutine. So I'm going to say ugen, okay, ugenerator. It needs some arguments. I'll figure out what argument it needs later. So it will need a few things. It will need to know how many more trials is needed. Okay, so we'll have num trials, as one parameter, and then it also needs to know, what kind of choices have been used up at this point. Let me think. Yeah, it just needs to know what was the last available choice. Okay, so first available choice would be my second argument here. And since this is going to be recursive, I need to find out, when can I stop, right? Well, it's easy. When num trials is 0, then we're done. There's no need to do recursion here, because we have done all the trials already, and we can just print whatever the result is. So that's the other thing we need to do, is to pass the result along, which is going to be a string. So we have char star, this is the result. And we also need to know which position am I in? What is the current position? So we need another pointer for that. You can use a pointer or you can use an index. So which one do you want to use? I would just say, trial number. Okay. Array indexing looks a little bit friendlier compared to just using pointers. So these are the parameters. Let me just explain the parameters again. The first one tells me how many more trials, including this one, do we have to deal with in this experiment. The second one is telling me, of all the choices from A to Z, what is the first available choice to me? Okay. The third one is the beginning of a string, so that the last invocation, when we get to the base case and stop recursion, I know to print out the entire string. And then the last one is saying, if this is not done yet, what is the trial number? The first trial is trial number 0. The second trial is trial number 1, and so on. So I need to identify that in order to figure out which part of the string am I supposed to modify. Is that okay? All right. So if the number of trials is 0, that means there are no. I'm all done. Okay, the string has everything in it. So in that case, we can terminate the whole string. Which means trial number result trial number can be a null terminator at this point, and then we can just print it out. In plain C, we can use a put s, instead of printf. So we can just say print the whole thing, print result, and we are done. And the only thing I need to know is whether put s also appends an end of line. Okay, it writes a string and a new line to standard out, so I don't need to insert my own \n or the new line here. Okay, so we just have to handle the else now. So what the else is corresponding to is we still got more work to do. Okay, we have at least one trial left. Is that okay? But what are my choices for that trial? Well, it's going to be starting with first available choice, and we need to figure out. Okay, so there's a for loop. I know where we start. I just need to know. I also need to know where it ends. Okay, we'll work this out as we go. So I goes from first of available choice, and then we say I is less than last available choice. There we go. Last available choice. And we'll add that as a new parameter here. Last available choice. And this is actually how I write code. It's kind of like jumping around a lot, depending on, oh, I think I need one more thing, go back, add another parameter. And most of my students have learned not to copy everything that I type because they know that I'm going to insert something, change something along the way. Okay, there we go. So this is a for loop, and inside here we say result bracket trial number, which is my trial, okay, gets a plus whatever I is. So quote a quote is really just a shorthand for the ASCII code of lowercase a. So when you add I to it, that will, if I is 2, then you have C instead of A, because the ASCII code of C is 2 away from A. So this is how I change what I choose for this particular trial. And then what we do is we do the recursion, ugen, okay? And ugen is going to pass num trial -1 because I just handled one of the trials. It's going to pass the first available is I now because I have used up that choice, okay? And then last available would still be the same. Even last available choice is still the same. And result is still the same because that's the beginning of the string, which I don't want to change. But trial number needs to be +1 because now the next trial has a higher trial number, which is 1 more than what I have. So that's the recursion right there. Are we still doing okay so far with this? Okay. All right, so when we call this from the beginning, from main, we have to pass number of trials. First available choice is going to be 0 because that is representing everything is available. And then the last available choice is going to be number of choices in the main program. Is that okay? Yes? Okay, all right. So we go to here, and then we now make the call. And of course, I cannot remember the ordering of the arguments. That's okay. That's why we got split. So we can look at the the function definition on one side, and then we can call it on the other side. So we say ugen, and then we say num trials, which is the local variable over here, and pass along 0 as my first available choice, num choices as my last available choice, and I need a local string in this case, char result string. 27 is more than enough, right? It can only be as much as 27. No, 27, because you have 26 actual letters plus the null terminator. So 27 is what we need. So we pass result string along, and then the first trial has a trial number of 0. So that's how we start the whole thing. Are we doing okay so far? Now there is one more thing I need to do, okay, which is sometimes I run out of choices. In other words, first available choice is the same as last available choice. So in that case, that means there's nothing we can do here because I'm out of choices. So in that case, I need to remember not to do the recursion, and it's not going to do the recursion because of the condition. Because when I is initialized to first available choice, and first available choice turns out to be the same as last available choice, that means this condition will fail without getting into the body of the loop, which means it won't go into the recursion, which is what I want. Okay. All right. So are we ready to take a look at how this works? Because you guys cannot wait to see how my program fails, right? I cannot wait either. If it fails, it's good because then I can teach you how to debug a program too. So let's hope it does. So GCC-O, well, we'll do a -G just in case I need to debug it. -1 all, -O to specify the actual output name of the executable, and then U.C, which is the name of the source file. And we got a few things wrong here. Okay. Implicit declaration of functions put as, okay, let's fix that first. And then we have num trial undeclared. Okay, that's a Prologue. Okay, I used the wrong name. Okay, so minor stuff. Man put as, where is it found? stdio.h. Okay, there we go. And then the other one was num trial, but not an S after that. So we say bracket S here. So this is why I like VI or tools that accept regular expression, because what I'm looking for, because I know I misspelled num trials as num trial without the plural, right? So I'm looking for a pattern of num trial, but it is not a lowercase s that is the end character after num trial. That should get me to the line where I did a misspelling, and it's right here, and there's only one of them. Now I could have substituted it too, like fix the error with one single command and say replace num trial without an s with num trial, right? But this is okay. Huh?
That's pretty nifty. I mean, that's awesome. You have to be running a lot of recurrence.
No, you don't. You can install VI in Windows.
Okay.
It's easier to search.
Hmm?
It's easier to search and find.
Yeah, once you learn how to use regular expression, it's really, really handy. And you don't have to learn the most complicated, most convoluted syntax first. You start with something simple. And then you go like, oh, okay, but I need to look for things that have any number of blah, blah, blah. Then you can start to get a little bit longer and more complex. So you can learn how to do regular expression on a kind of, gradually and not really, learn all the most difficult way to use it the first time. All right, so let's just run U without a debugger. Oh, I need to give it parameters, right? And I already forgot, which one is which one, so I'm gonna have to look it up. The first one is the number of trials, and the second is the number of choices for the first trial. So implicitly, we kind of know that the first argument has to be less than the second argument. It doesn't make sense when you have more trials than there are choices, because each trial takes one choice, and if you have more trials than there are choices, then it's not going to print anything. Now, you might say, but Tex, your program did not check for that condition. So what happens if you give it the wrong kind of parameter and specify more trials than there are choices? What do you think this program is going to do? Does it get into an infinite loop? Does it crash? Or does it just print nothing because there's no way to make this happen? It should be the third option. Okay, so let's check it out. Okay, so we'll run it and say there are 4 trials and there are only 2 choices. No. Because I forgot a +1. Okay, that's why. Okay, I forgot a +1.
Off by 1.
Hmm?
You're off by 1.
I'm off by 1. There we go. What I have chosen, you cannot use as the next trial. Right? So I think that would fix the problem.
When he wrote just
What?
when you wrote that, I was like, what?
Is that okay now?
Yeah. I think
Okay. All right, so let's run that. Nothing. Okay, that's the way it's supposed to be. Okay, what about 4.4? In other words, I have 4 trials. That's what the first 4 is, and then the second 4 says, we want to have. I'm only giving you 4 choices. How many lines should it give me? It's 4. Choose 4. It's 1, and what it would be A B C D. Should be A B C D. So let's check it out. It just gives me A B C D. Okay, let's try something where something like 2, 4 2. I have 4. No, the other way around. 2 4. Okay. So we have 2 trials and 4 choices to begin with. So it becomes 4 choose 2, right? So 4 choose 2 is 4 factorial divided by 2 factorial times 2 factorial as the denominator. 4 factorial is 4 times 3 times 2 times 1, which is 24. And then 2 factorial is just 2, okay? So you have 2 factorial times 2 factorial. You have 2 times 2, which is 4. So 24 as the numerator, 2 times 2 as the denominator means we should end up with 6 rows, right? And we have exactly 6 rows. We have AB, AC, AD, BC, BD, and then CD. So there we go. Not quite 3 minutes. As somebody said earlier. Yeah, it would only take you 3 minutes. What is that with or without time dilation? Am I moving near the speed of light?
I said if you're overclocked. You, not your computer.
Okay, but is that okay? Does everybody understand the program and how it works? Why it works the way it does? Okay. So yeah, go ahead. Counting? We use counting already in the second exam. It's not going to be, at least not by itself, in the final exam. For instance, I give you a graph, and I might ask you, so how many paths exist between this vertex and that vertex? So depending on the configuration of the graph, what you learned about permutations and combination may come in handy. So there's that. Okay, so are there any other questions about this particular program? And this is way easier than generating all the permutations, because if you want to generate all the permutations, you actually need a set representation. You actually have to know, oh, this has been used, that has been used, that has been used, but everything in between I can use. So that's a little bit more, tracking and, a little bit more work, because you have to first, get the set representation in, which is not really too bad, because, set representation, when your entire set can only have up to 26 items, is pretty easy. And you just use a bitmap representation, which means each bit of an integer is representing the presence or absence of a particular element. But it will still take a little bit of work to get that part to work first, and then you build upon that portion. But when you're looking at combination, it's pretty easy, because we can just use the implicit ordering to tell me what choices I have left. Yep.
Go back to your congenital.
Sure.
See the parameters of the function again.
The parameters. Oh, you mean this part?
Yes.
Okay. And the recursion part is the most important part here. This is the most important part. It's how does this invocation relate to the next invocation? What is changed? Yep.
So why is it I plus 1 again?
It's I plus 1 because in this invocation, I have used up that choice. So it should not be available to the next one. And that's why if I did not do the I plus 1, then it gave me those AABB, AABB, AAAB, and so on.
Yeah, because I thought you were incrementing it, but I forgot to increment it.
Right. And you can also see that without recursion, this would be kind of difficult to write. How many people used global variables in this program? And what did you use the global variable for the string for the result? And that's why you need a global.
I made an array of letters so that it used those
Okay.
captures.
So you made an array of letters to choose from, right? To map the index into what you're supposed to print.
Yeah, so that I could write the program using like numbers and then have them select
Gotcha.
them.
Okay. So basically, I instead of using an array of characters, I use this trick to do pretty much the same thing. Okay. And by the way, if you do it in C++, you automatically have used a few global variables already, because C in and C out are global variables. Huh? You did in C. Okay, very good. All right. Any other questions about this particular program? Any other homework assignment you want me to review or talk about?
Was there a homework assignment you didn't review or talk about?
I don't remember.
How about that family tree this year?
Which one?
He should review the family tree quiz.
What? The family one? Time travel, right?
I tried to do it at the beginning of the semester, but I didn't understand.
Hmm?
It's like really blew your mind.
Which one?
Oh, I tried to do it at the beginning of the semester, but I didn't understand.
Oh, the cousins one, or
Oh no, the prologue one.
oh, the prologue one? I see. All right. Really, there are no other questions about the material? Well, we can start with practice final then. Any objection to getting the practice final started earlier than next Monday?
How about two practices?
Well, we'll see how much we can pack in about 15 minutes, right? That's all the time we have today.
Take your time. No rush.
Yeah.
Class on Wednesday, right?
Huh?
Is that the class on Wednesday?
Oh, that's a good question. I'm going to look it up and confirm. So we have ARC final exam schedule. I just want to be sure. Okay, so according to this, the final exam week starts from the 16th, so that means the 15th is still an instruction day, so we do have class on the 15th. And today is the 8th, so that means next Wednesday we still have class. So we have Monday and Wednesday for lecture, which means it's good because we can start on the final exam review on Monday. Well, we're going to start in a few minutes, but we have 2 entire classes to go over final exam questions.
So we have our finals on Monday, which begins at 12:45.
Let's see. So this class starts exactly at noon, and it's a Monday, Wednesday class. So we're going to have our final exam on the 20th, and the start time is 12:45. Right here, 12:45 to 2:45 on the 20th, which is the Monday after next Monday. So we have, so after the review, we have 1 week before the actual final. Yep.
Are we allowed to come a little bit early?
To jumpstart.
Or like, do you just start at 45?
I cannot get the room until 12:40-ish, and I cannot start, until 12:45, because since this is the published time, some people may have, scheduled their other activity already. So it would not be fair if I say, okay, if you can come early, I'll give you a head start. That would not be fair to people who have already scheduled and go like, well, I'm assuming it's going to start at 45, and I put some other things already scheduled, ahead of the class. So I cannot, have some people to start early. Now, it also means that if people come after 12:45, they cannot get that time back, because this is already published since the beginning of the semester. So I think everybody should have schedule around this time for other things. Okay. Any other questions about the time of the final exam? The place is going to be here. Okay, so we're going to have the final exam in the same classroom. It's going to be the same rules. Okay, open book and open notes. Yep.
Normally, how many questions?
Haven't decided yet. It depends on how involved each question is. So if the questions are long and time consuming, I will have fewer of those. And if I ask simpler questions, for instance, I can make simpler questions by giving, instead of having you guys to trace, I can give you a trace that is flawed. And instead I will ask you, okay, which line is wrong? Fix that. Or fix the lines that are wrong, and so on and so forth. Or things that are missing, fill in the things that are missing. So that would not take nearly as long as having you guys to actually do the entire thing. Because if you were to do the entire thing, just writing is going to take a lot of time. But if you're just checking, it doesn't take as much time, in theory. And I promise to print in a legible font, not robot or barcode type of font. That would be kind of funny.
Binary.
Barcode, QR code. This QR code is the entire question. Open phone. No, no electronics. You have to decode QR code manually.
No.
42.
That would actually make a very good question for an algorithm class. Because if I show you the algorithm of QR code, how it's made, then you can kind of look at the QR code and decode it back into the text string that it is representing. Yep.
I was completely about to ask you exactly how you decode it.
I have not read up on the QR code page on Wikipedia. QR code is actually interesting. I know I'm kind of digressing away from the final exam, but QR code is interesting because it has redundancy. In other words, if you take a QR code thing, and then you take a pen and then you scratch out certain pixels, depending on how much you scratch out, it might still work. It actually has redundancy built into it, so it doesn't need to be perfect in order for a machine to read the actual QR code. And I haven't really looked into it. I just know that it has redundancy built into it, which is kind of cool. All right, so let's go ahead and take a look at the exam questions from past semesters. And that's a pretty handy way to, have a review session. Because I don't have to make actual, just questions for the practice, session. I can just go to, old exams and go like, okay, let's use those as, practice exam questions. All right, so these are really old. Let's not use those. And then we have, let's see, it's all the fx's. So this is one that we can look at. I think that's a more recent one. Or do we? Okay, I'll post the one from last semester.
I think you have two long things.
Oh, okay, all right, that works. So let me see.
Spring 2019 one.
It is not. Does not exist yet. Compile time error, variable not found. Or more appropriately, my office building number 404 not found. Okay, so you said that some of those are posted already, and that's spring 18. So it's the same thing. Well, we can look at this. Yeah, that's spring 18, because it's 18 spring, FX, final exam. And can I make this bigger? No. Can I pull out that? Yeah. Hmm? Yeah, we can just do it this way too. Just use a local viewer. There we go. Okay. And we can get rid of that. All right, so the first part is something I mentioned already: open book, open notes, open material, but it's only limited to printed material and things that are handwritten. Okay, and it has to be prepared before class. because I don't, as I said, I might have mentioned it, I may not have mentioned it, because I don't want people to write down something and pass that paper along to another person and go like, but you said everything that's handwritten or printed is okay. No, it's only the material that is done before class. It has to be prepared before class, before the exam. Also, make sure that you bring some extra pieces of paper if you think you might need those, because I may not have any extra paper for you. If you think that you might need to do a trace and a ruler is going to be handy to line everything up, bring your ruler. Okay, it's not expensive. Or do you guys want me to go to Dollar Tree and buy a whole bunch just in case? I used to go to the Dollar Tree and buy those $1 calculators and bring a whole bunch in a bag in case someone says, I need a calculator. Okay, here's.
Just throw the bag at it. There's a bag.
The bag is more expensive. Okay, so this is the definition of one graph for a question, and I spell out the A-star algorithm. I tend to do that just in case people do not have the algorithm handy, or I choose to use a slightly modified algorithm compared to what we talk about in class. So you have to be careful and follow the algorithm actually in the test. Okay, so got to be careful about that.
Will you say if you use a different version of the algorithm?
Huh?
Will you say if you use a different version of the algorithm?
I'll say it and say that this algorithm is close but not exactly the same as the one we use in class. So the algorithm is given to you, and this is the actual first question. So the actual first question really is just a trace. I mean, that's all it is. It's very close to the homework assignment, except this applies to the A-star algorithm instead of the Dijkstra's algorithm. Okay, so both can be in the test in the final exam. So even though we only did the homework assignment on Dijkstra's algorithm, you have to be able to trace A-star as well. Okay, to prepare for the exam. So this is just a trace. I give you all the given stuff, and that's it. And I think in this one I gave people a table, so they can just use the table. So that makes it kind of easier because it's already pre-lined, and you just have to kind of fill in the things. So for the G, F, and pref values, you just kind of do the elements here, all the vertices, like that, and then have sub-items in those columns. And that's why a ruler would be handy for this purpose. Okay, so that's question number one, just a trace. If you know the algorithm and you're careful in your steps to trace the algorithm, you'll be fine. If you make a stupid mistake somewhere, okay, it's not going to be the end of the world. I do not just check the final answer against the key and say, okay, if this is wrong, I give you 0 points. I try my best to see whether you understand and follow the algorithm. So if you make a mistake and the final answer is not entirely correct, I will look at the steps that you did show in the trace and use that for partial credit purposes. Okay. Question number 2. So question number 2 says the construct called pref in the A-star algorithm can be seen as a function, blah, 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 for the entire duration of executing the while loop. Describe what makes a set of 2 tuples a function. So this is getting back to the definition of functions. So you have to remember that, okay? Or have it on a piece of paper. I think last year I even said to people, if you have the definition of a function and can answer this question because it's actually on your sheet of paper, you can cut and paste it physically onto the answer and go like, yes, I know, because this is what I have prepared to take with me as my material.
We bring the notes and cut out what you said the definition of function
Yes.
is. Can we do that?
Yes. Yes. So now you have to bring a pair of scissors and Scotch tape or glue.
Put down a little audio recorder so you write down the button.
Or better yet, you can print all my notes on how do you call those things? The print labels, the self-adhesive label stuff. So now you can cut off any piece and just kind of peel off the back and go, here's your answer. Next, describe why pref is a function before the first iteration of the while loop. And last, describe why pref remains as a function despite the update of the set on line 18 of the algorithm. So now that really gets a little bit more involved because you have to look at line 18 and say, how are we preserving the properties of a function? Okay, so that's one question. We are running out of time. This is question number 3 of 5, and it's also related to A star. So it's going to be heavier on the topics that we started to talk about after the second exam. And next week, on Monday, I'll give you a better idea of, what other stuff other than, the graph algorithms I would include in the exam. All right, so have a nice weekend and try to use this time to look at the previous final exams so that when we talk about those, you have an idea of what we are talking about.